Welcome to this problem-solving session. Today, we'll be tackling problem number 1030, titled Matrix Cells in Distance Order. We'll explore the problem statement, break it down step by step, and review different approaches to solve it effectively. Let's dive in. The problem asks us to work with a matrix, defined by the dimensions rows and cols. We are also given a specific cell in this matrix, located at R center, C center. Our goal is to return a list of all the cells in the matrix, ordered based on their Manhattan distance from this center cell. Manhattan distance is a way to measure the distance between 2 points in a grid. Specifically, it's calculated as the sum of the absolute differences between their row indices and their column indices. For example, the Manhattan distance between two cells, R1, C1, and R2, C2, is given by the formula R1, R2 plus C1, C2. Ultimately, the output should be a sorted list of pairs, R, C, where each pair represents the row and column indices of a cell in the matrix. The output format for this problem is a list of lists or tuples, where each inner element contains two integers representing the row and column of a matrix cell. This list must be sorted in ascending order of the Manhattan distance from the given center cell, R center, C center. If two cells have the same distance, their relative positions in the output list can be in any order. To clarify this, let's look at the first example. Here, the input specifies a 3x3 matrix with the center cell at 0, 0. The output should list all the cells, starting with the center itself, followed by other cells in order of increasing Manhattan distance. The result is 0, 0, 0, 1, 1, 0, 0, 2, 1, 1, 2, 0, 1, 2, 2, 1, 2, 2. In the first example, the matrix is 3 times 3, and the center cell is 0, 0. To compute the Manhattan distances, we calculate the difference in row and column indices for each cell relative to the center. For instance, the distance from 0, 0 to itself is 0. For 0, 1, the distance is 1 because the row difference is 0 and the column difference is 1. Similarly, 1, 0 also has a distance of 1. For cells further away, like 0, 2, the distance is 2, since the column difference is 2. Continuing this process, we calculate the distances for all cells, resulting in distances ranging from 0 to 4. Sorting the cells by these distances gives the final output. In the second example, the input describes a 2x2 matrix with the center at 0, 1. For the second example, the matrix is 2 times 2, and the center cell is 0, 1. The Manhattan distances are calculated as follows. The distance from 0, 1 to itself is 0. For 0, 0, the distance is 1, since the row doesn't change, but the column difference is 1. Similarly, 1, 1 also has a distance of 1, as the column is the same, but the row difference is 1. Finally, the distance to 1, 0 is 2, because both the row and column differ by 1. Sorting these cells based on their distances, we get the output 0, 1, 0, 0, 1, 1, 1, 0. Now, let's look at the third example, which involves a smaller matrix. In the third example, the matrix is 1 times 2, which means there is only one row and two columns. The center is at 0, 0. The distance to the center itself is 0, and the distance to the other cell, 0, 1, is 1, as the row difference is 0 and the column difference is 1. Since there are only two cells, the output, when sorted by distance, is simply 0, 0, 0, 1. These examples demonstrate how to calculate Manhattan distances and sort the cells accordingly. Now, let's consider some edge cases and constraints. There are several important edge cases to consider. First, if the matrix has the smallest possible dimensions, such as rows equals 1 and cols equals 1, the matrix contains just one cell, which is also the center. For example, if the input is rows equals 1, cols equals 1, R center equals 0, C center equals 0, the output would simply be 0, 0. On the other hand, the problem must also handle the largest possible matrix dimensions of 100 by 100, where there are 10,000 cells. In such cases, the solution must be efficient to avoid performance issues. Another scenario is when the center is at the edge of the matrix. For instance, with rows equals 5, cols equals 5, and the center at 0, 4, the solution must still correctly sort cells by distance. Finally, the solution must work for non-square matrices, such as rows equals 3 and cols equals 7. Regardless of the matrix shape, the logic for calculating distances and sorting the cells remains the same. To solve this problem, one of the approaches we can consider is a brute force method that sorts the matrix cells based on their Manhattan distance from the given center. The Manhattan distance is calculated using the formula x1 x2 plus y1 y2, which gives us the total number of moves needed to go from one cell to another in a grid-like structure. Here, we start by generating a list of all cells in the matrix using nested loops. Once we have all the cells, we compute the Manhattan distance for each one relative to the center point, R center, C center. After calculating these distances, we sort the list of cells based on their distances. Finally, this sorted list is returned as the result. While this method is simple and straightforward, its time complexity is dominated by the sorting step, which makes it less efficient for larger matrices. Specifically, generating all the cells takes O, rows asterisk cols, and sorting them takes O, rows asterisk cols, asterisk log, rows asterisk cols, resulting in an overall time complexity of O, rows asterisk cols asterisk log, rows asterisk cols. Additionally, the space complexity is proportional to the number of cells, O, rows asterisk cols. Now, to address the inefficiencies of the brute force approach, we can consider an optimized method that uses bucket sort instead of traditional sorting. The key insight here is that the maximum possible Manhattan distance in the matrix is predictable. It's given by rows plus cols, 2. With this in mind, we can create buckets for each possible distance value, ranging from 0 to this maximum distance. As we iterate through each cell in the matrix, we calculate its Manhattan distance and place it in the corresponding bucket. This eliminates the need for sorting, as the buckets inherently group cells by distance. Once all cells are distributed into the appropriate buckets, we simply flatten the buckets to generate the final ordered list of cells. This approach is particularly efficient because it avoids the computational overhead of traditional sorting. Instead, the time complexity is reduced to O, rows asterisk cols, for both generating cells and flattening the buckets, making it better suited for large matrices. Looking at the complexity of the bucket sort approach, we see that it performs very efficiently. Generating all cells in the matrix and placing them into their respective buckets takes O, rows asterisk cols, and flattening the buckets to produce the final result also takes O, rows asterisk cols. This gives the approach an overall time complexity of O, rows asterisk cols. For space complexity, we use additional space to store the buckets, which requires O, rows asterisk cols, as well, since each cell must be placed into a bucket. While this does require some extra memory compared to the brute force method, the trade-off is well worth it for the significant reduction in time complexity. After evaluating both methods, we chose the optimized approach because of its scalability and linear time performance. The primary reason this method works so efficiently is that we leverage the predictable range of Manhattan distances in the matrix, allowing us to group cells directly without sorting. In this problem, a few key observations helped us arrive at the optimized solution. First, the linear growth of Manhattan distance with respect to row and column differences makes it highly predictable. This predictability allows us to predefine the size and structure of the buckets, eliminating the need for dynamic sorting. Second, the maximum possible distance in the matrix is easy to calculate, which simplifies the setup of the bucket sort process. This method ensures an efficient and stable way to order the cells, even for very large matrices. Comparing the two approaches, the brute force method is easier to implement but becomes impractical for large inputs due to its sorting step. On the other hand, the optimized bucket sort approach requires additional effort for setup but is significantly faster and scales much better. While the performance difference may be negligible for smaller matrices, the optimized method truly shines as matrix size increases, making it the superior choice for this problem. In this problem, we're tasked with sorting all the cells of a grid based on their Manhattan distance from a given center cell. To begin, we need to initialize the grid. This involves creating a list to store all the cells, where each cell is represented as a pair, R, C, with R being the row index and C being the column index. We loop through every row and column within the grid dimensions, appending each cell to this list. Once we have all the grid cells, we move on to computing their Manhattan distances. The Manhattan distance measures how far a cell is from the center cell, considering only horizontal and vertical movement. The formula for this is abs, r center, plus abs, c center, where the absolute differences calculate the distance in each direction. This simple formula helps us quantify the closeness of each cell to the center. Now that we can compute Manhattan distances, the next step is to sort the cells based on these distances. Most programming languages provide efficient built-in sorting algorithms, which we can leverage here. For instance, in Python, we can use the sorted function with a key that calculates the Manhattan distance for each cell. This ensures that cells closer to the center, with smaller distances, appear earlier in the sorted list. After sorting, the result is exactly what we need, all grid cells arranged in order of increasing Manhattan distance. Finally, we return this sorted list. The key insights here are the use of Manhattan distance to determine proximity in a grid and the role of sorting to achieve the desired order. While generating the grid takes O, rows * calls, time, sorting adds O, n * log, n, complexity, where n is the total number of cells. Together, these steps efficiently solve the problem. To implement this algorithm, we rely on a few key data structures and operations. First, we use a list to store all the grid cells, as it allows for straightforward iteration and sorting. The sorting itself is handled by the built-in sorting algorithms of the programming language, which are both optimized and efficient. As for the key operations, grid traversal ensures that no cells are missed as we iterate through all rows and columns. The distance calculation uses absolute differences to accurately measure distances, even when indices are negative. Finally, sorting ensures that the output respects the required distance order. Together, these choices make the algorithm both simple and effective for the problem at hand. When applying this algorithm, it's important to consider edge cases. For example, in a single-cell grid where rows and calls are both 1, the result will only contain the center cell. If the center cell is located at the edge of the grid, the algorithm still works seamlessly because distance is calculated independently for each cell. Non-square grids, such as rectangular ones, are also handled naturally since the algorithm iterates over all rows and columns without assuming equal dimensions. From a time complexity perspective, initializing the grid takes O, rows * calls, time, while sorting adds O, n * log, n, where n is the total number of cells. This gives an overall complexity of O, rows * calls * log, rows * calls. In terms of space, we need O, rows * calls, to store the list of cells and additional space for sorting, which is typically O, n. The algorithm is therefore efficient in both time and space for this task. This solution addresses the problem of returning all cells in a grid sorted by their Manhattan distance from a given center cell, R center, C center. The Manhattan distance is calculated as R1, R2 plus C1, C2. The function allCellsDist order begins by generating all possible cell coordinates in the grid using a nested list comprehension. The outer loop iterates over all rows, 0 to rows 1, and the inner loop iterates over all columns, 0 to calls 1. Each cell is represented as a tuple, R, C. Next, the cells list is sorted based on Manhattan distance from the center cell, R center, C center. This is achieved using the sort method with a custom key function. The key function computes the absolute difference in rows and columns between each cell and the center cell, summing these values to determine the Manhattan distance. Finally, the sorted cells list is returned. This solution is efficient and concise, leveraging Python's built-in sorting capabilities. The time complexity is O, rows * calls * log, rows * calls, due to the sorting step, and the space complexity is O, rows * calls, to store the list of cells. Here, we start by importing the necessary packages, including java.util** for utilities like lists and sorting. The method allCellsDist order takes 4 parameters, the number of rows and columns in the matrix, as well as the coordinates of the center cell, R center, and C center. Step 1 of the implementation involves generating all the cells in the grid. To do this, we iterate through each row and column using nested loops. For every combination of row and column indices, we create a cell represented as an integer array and add it to a list called cells. Once we have all the cells, step 2 is to sort them based on their Manhattan distance from the center. We use the collections.sort method and provide a custom comparator. The comparator calculates the Manhattan distance for each cell by summing the absolute differences of their row and column indices from those of the center. It then compares the distances to determine the order. This ensures that cells closer to the center appear earlier in the list. Finally, step 3 converts the sorted list of cells into a 2D array. We initialize a 2D array called result, with dimensions matching the size of the cells list. Then, using a simple loop, we copy each cell from the list into the corresponding row of the result array. Once all the cells are transferred, the result array, now sorted by distance, is returned as the output of the method. This completes the implementation, effectively generating the required list of cells in the correct distance order. To solve this problem, we start by generating all the cells in the grid based on the given dimensions. For this example, we are working with a 2x3 grid, and the center point is specified as 0, 1. Using a list comprehension, we systematically iterate through every row index from 0 to 1 and every column index from 0 to 2. This produces a complete list of all cells in the grid: 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2. Next, we calculate the Manhattan distance for each cell relative to the center. The formula for this is abs, r center, plus abs, c center. For example, the distance for 0, 0 is 1, while the distance for 0, 1 is 0 since it's the center itself. After calculating distances for all cells, we can sort them based on this distance value. Once the Manhattan distances have been calculated for all the cells, the sorting process begins. For example, the cells 0, 0, and 0, 2 both have a distance of 1, while 1, 0, and 1, 2 have a distance of 2. After sorting all the cells by their distances, we get the order 0, 1, 0, 0, 0, 2, 1, 1, 1, 0, 1, 2. This is the final output for this example, where every cell is listed starting from those closest to the center and moving outward. With that, we have completed this first example, and the result matches the expected output. Now, let's consider a square grid of size 3 by 3 with the center located at 1, 1. First, we generate all the cells using the same approach as before. The grid's dimensions mean that we include all row indices from 0 to 2 and all column indices from 0 to 2. This results in the list of cells 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. Again, we calculate the Manhattan distance for each cell relative to the center. For instance, the distance for 0, 0 is 2, while the distance for 1, 1 is 0 because it is the center. Once all distances are computed, we proceed to sort the cells by these distances. After calculating the Manhattan distances, we sort the cells based on their proximity to the center. For this grid, the sorted list becomes 1, 1, 0, 1, 1, 0, 1, 2, 2, 1, 0, 0, 0, 2, 2, 0, 2, 2. Notice how the center cell, 1, 1, appears first as it has the smallest distance of 0. Cells that are equally distant from the center are grouped and appear in the order they were originally encountered. This ordered list represents the final output for this example, where we systematically move outward from the center. Finally, let's look at a single row grid of size 1 by 5, where the center is located at 0, 2. As before, we start by generating all the cells in the grid. Since there is just one row, the cells are simply 0, 0, 0, 1, 0, 2, 0, 3, 0, 4. We calculate the Manhattan distance for each cell relative to the center. For example, the distance for 0, 0 is 2, while the distance for 0, 2 is 0 as it's the center itself. Sorting these cells by distance gives the order 0, 2, 0, 1, 0, 3, 0, 0, 0, 4. This is the final output for this example, and it demonstrates how the solution handles grids with only one row. To analyze the time complexity of our solution, we need to focus on the two main steps involved. The first step is generating all the cells in the grid. The grid consists of rows *call cells, and we use a nested list comprehension to iterate over every row and column index to create a list of these cells. Since we visit each cell exactly once during this process, the time complexity for this step is O, rows *calls. The second step is sorting these cells based on their Manhattan distance from a center point, R center, C center. Calculating the Manhattan distance for a single cell, which involves the absolute difference of its row and column indices from the center, is an O(1) operation. However, sorting the entire list of rows *cols cells requires O rows *cols *log rows *cols time due to Python's timsort algorithm. This sorting step is the more computationally expensive of the two. When we combine these steps, the overall time complexity becomes the sum of the two, O rows *cols for generating the grid and O rows *cols *log rows *cols for sorting. Since the sorting step dominates, the final time complexity of the solution is O rows *cols *log rows *cols ***. Now, looking at space complexity, we must first consider the space used to store the list of all cells. The cells list contains rows *cols elements, and each element is a tuple, R, C, representing a cell. Since each tuple requires constant space, the space required for the list is O rows *cols. Additionally, the sorting operation uses Python's timsort algorithm, which requires O, n, auxiliary space in the worst case, where n is the number of elements being sorted. In our case, this results in an additional O rows *cols space. Therefore, both storing the grid cells and the sorting overhead contribute to the total space complexity. By combining the space required for storing the grid cells and the auxiliary space used during sorting, the total space complexity of the solution is O rows *cols ***. Now, let's evaluate the best, average, and worst case scenarios. Since sorting is deterministic and always involves O and *log n operations, there is no best case improvement in this solution. On average, the time complexity remains O rows *cols *log rows *cols, with cell generation taking O rows *cols. The worst case performance is the same as the average case because both cell generation and sorting are deterministic and do not vary based on input. This consistency ensures that the solution is efficient and predictable across all cases. If we compare this solution to a naive approach, we can see significant improvements. A naive method might involve iterating through each cell repeatedly to calculate distances and dynamically ordering them, for example, by using a priority queue. This would result in a much higher time complexity of O rows *cols (2) due to the frequent reordering operations. In contrast, the current implementation avoids this inefficiency by leveraging an optimized sorting algorithm, reducing the time complexity to O rows *cols *log rows *cols ***, which is ideal for this problem. Mathematically, we can confirm this by analyzing each step. Generating the grid cells involves rows *cols iterations, with each addition to the list taking constant time, leading to a complexity of O rows *cols. Sorting these rows *cols elements with timsort is O and *log n, where n is the number of elements. Even accounting for the constant time distance calculations during sorting, the asymptotic complexity remains unchanged. Consequently, the total time complexity of the solution is firmly established as O rows *cols *log rows *cols ***. When solving this problem, there are a few common mistakes to watch out for. First, many confuse Manhattan distance with Euclidean distance. Remember, Manhattan distance is calculated as the sum of absolute differences, which is x1 x2 plus y1 y2. Euclidean distance, on the other hand, involves squaring the differences, summing them, and then taking the square root, sqrt, x1 x2 2 plus y1 y2 2. Using the wrong formula will lead to incorrect results, so it's crucial to confirm the distance metric specified in the problem. If Manhattan distance is mentioned, avoid any square root calculations entirely. Another mistake involves oversorting the data. Sorting the entire dataset to find the k closest points is inefficient, with a time complexity of O n *log n. Instead, you can use more optimal methods, like a heap or quick select, which reduce the complexity significantly. Lastly, don't overlook edge cases. For example, if k is greater than the number of points, or if there are duplicate points or identical distances, these scenarios can cause runtime errors if not handled properly. Make sure to validate inputs and use secondary criteria for sorting when distances tie, such as the coordinates themselves. Another mistake to avoid is failing to use absolute values correctly. Since Manhattan distance relies on absolute differences, omitting the absolute function can lead to errors, particularly when working with negative coordinates. Always make sure to use abs to handle negative values properly. Additionally, brute force iteration can be inefficient. Iterating over all pairs of points can quickly become computationally expensive, especially when the problem only requires the k closest points. Instead of comparing every possible pair, optimize your approach by focusing on efficient data structures like heaps or applying divide and conquer techniques. These strategies will significantly improve your solution's runtime while still ensuring accurate results. From an interview perspective, this problem often boils down to a variation of the top k problem, where the goal is to efficiently identify the k smallest or largest elements in a dataset. To approach this, you should understand when to use a max heap versus quick select. A max heap has a time complexity of O n asterisk log k, making it great for dynamically maintaining the k closest points. Quick select, on the other hand, has an average time complexity of O n, and is useful for directly partitioning data around the kth smallest element. It's also important to clarify the distance metric early in the discussion, as Manhattan and Euclidean distances require different implementations and may impact runtime. As you explain your approach, highlight the trade-offs between brute force, heap-based, and partitioning techniques, emphasizing how constraints like the size of n and k influence your choice. Finally, you can connect this problem to real-world applications, such as clustering algorithms like k-nearest neighbors, which often involve similar calculations of distance between points. This problem shares similarities with other well-known LeetCode problems. For example, in problem 973, k closest points to origin, you identify the k points nearest to the origin using Euclidean distance. Problem 658, find k closest elements, focuses on finding the k integers closest to a target value, while problem 215, kth largest element in an array, is another variation of the top k problem. Additionally, problem 1499, max value of equation, incorporates Manhattan distance in maximizing a function. When considering alternative approaches, brute force sorting is straightforward but inefficient for larger datasets, with a time complexity of O n asterisk log n. Using a max heap is more efficient for finding the k closest points, as it maintains only the k farthest distances in the current set, reducing the complexity to O n asterisk log k. Quick select is often the fastest option, with an average runtime of O n, though it can degrade to O n squared if pivot selection is poor. For grid-based problems, advanced techniques like bucketing points by distance can optimize runtime further, though they may require additional space. Understanding these trade-offs and tailoring your approach to the problem constraints is key to crafting an efficient solution. Great job! We covered problem number 1030 by sorting matrix cells based on their Manhattan distance. We emphasized key concepts like distance calculations and sorting efficiency. Keep practicing and applying these techniques to similar problems. Don't forget to like, share, and subscribe for more content. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!